Suppose you have y, some function of x. I'm not going to tell you what it is, it doesn't matter what it is. And at some point, you know certain characteristics about the first derivative and about the second derivative. Okay? So, for instance, suppose you knew that the first derivative was negative. Okay, so for negatives, what would that tell you about the graph? Like that's an algebraic statement. Geometrically, what does it tell you? If the first derivative is negative. I've heard it. I'm just wondering how confident people are. It's decreasing, isn't it? It's going down. Something like that, or whatever. Okay, fine. That's okay. What about if the first derivative is 0? It's a stationary point. Okay? And there's a few different kinds of stationary points, aren't there? Right? So you could draw it as a horizontal point of inflection, or it could be a max, it could be a min, whatever. Okay? That's fine. Naturally, if the first derivative is positive, you get an increasing function. Okay. No problems so far. Now, that's because the first derivative tells you about the gradient, because it's the gradient function. The second derivative doesn't tell you about the gradient. It tells you about concavity. Okay. So, let's see how we are with pattern recognition. If I get the second derivative being negative, what does that tell you? Okay, concave down, right? So something like that. Or something like that. Well, really for this, it would actually be something like that. They're all concave down, aren't they? If you poured water on them, they wouldn't stay. Okay. All right, I'm going to skip this for a second. What if the second derivative were positive? It's concave up. Okay. Concave up. No dramas. Now, if the second derivative is equal to 0, pause for a second. I want you to recite in your head what that tells you about the graph. Just say it in your head in the quiet of your own mind. Okay. Now that you have it there, I want you to say it all out loud at the same time. Count of 3. Okay, are you ready? You got it in your head? Prepared? Commit? Okay, on the count of 3. 1, 2, 3. Okay, alright. What happened? What happened? Now actually, in some ways, you're all wrong, okay? Because let me just follow this thing, okay? Decreasing, increasing. Is this one decreasing or increasing?
Nothing.
It's stationary, which is another way of saying it's not increasing or decreasing. Right? That's what stationary means. Okay? So therefore when you go concave down and concave up, this means it's not concave anything. It has no concavity. Okay? Now that's what it really means. I didn't ask anything about points of whatever or whatever. I'm just asking about what kind of behavior is it exhibiting. Okay? Now what does no concavity mean? What does that look like? Now you already, because a lot of you said points of inflection, you have a picture in your head, don't you? Okay, but no concavity is much simpler than that, right? Let me give you let's do science, because you get lenses, right? That's where you first meet the idea of concavity. So what does a concave lens look like? It's sort of like an hourglass shape, isn't it? Right? That's a concave lens. What's the opposite of a concave lens? Convex. Okay, so I suppose using our language, we would say that's like concave in. And this is like concave out, sort of. Okay. Now, what would it look like if you had a lens? Actually, it wouldn't be much of a lens, but anyway, that had no concavity. What would it look like? It would just look straight, wouldn't it? Okay. Which is why, if you take, say, I don't know, something really complicated like y equals x. Okay, what does that look like? You take the first derivative and you get 1, increasing. You take the second derivative, the derivative of 1 is 0. It's this straight thing. Are there points of inflection? No. No, of course not. Because there's no... What is a point of inflection? What is a point of inflection? It's when you go from one of these to the other. You have to change state in order to be a point of inflection. Now that's why some of you were, Pedro, you said possible, okay? But it's kind of like for a question like this, like why am I even thinking about whether it's possible or not? Of course it's a point of inflection. So therefore, what I'm trying to draw out is a lot of your, in your working, there was a question that talked about, there's a graph, I can't remember what the equation was, okay? But a lot of you have done this. You said this, then you said therefore, great. Okay, but it's not so, right? Please do not skip the fact that if you want one of these, okay, what you must establish is changing from this to that, or vice versa. Okay? That's why when you're going for these, there's no way to get around the table of values. Okay? You've got to test for that point. You know, suppose it was 1, and you've got to test to the left and to the right. Okay? Now, I did get a question. Do we actually need to put some numbers in here? Okay? Yes. Do you need to put numbers here?
Yes.
Yes, you do. But why? Why?
Because you can just guess whether it's point inflection.
Okay, because you can always just say, you know, most questions, you'll know in advance whether there is going to be a point of inflection or not. It'll be like, find the points of inflection. You're like, well, okay, I guess there are points of inflection, right? Or for max min, it'll be like, find where it is. So you already know that information, so you can't just say, yeah, that's what I'm expecting. Okay? The values have to be in there. Okay?